everyone. Welcome to the Metamaterial Industry Application Comms and Antenna session. My name is Fatemeh, and in this session, I'm the chair of the session. In this session, we have 4 speakers, and each of the speakers will present for 15 minutes. At the end, we will have 30-minute Q&A. The session will be recording and later on available on the KTN website. I'm sure all of you which are joining in this session are so excited about knowing about how the metamaterial can help the communication and antenna, especially because nowadays communication is one of our key parts in our life. The antenna is one of the most important part of wireless communication system and significantly affect the total energy consumption. The upcoming 5G and 6G introduce additional challenges to the antenna, but could also provide opportunity to use RF energy more efficiently. It would be interesting to know if metamaterial antenna can overcome to any of the current challenges in the communication session. Our 4 amazing speakers today will explain how they use the unique properties of metamaterial to overcome some of communication challenges. So without further delay, we'll now move on to the main speakers. If you have a specific question while they are presenting, please put them in the chat box, and we pick these up in Q&A session after all the presentation is finished. I'd like to introduce our first speaker, Dr. Mohsen Sazegar. Mohsen is a Senior Director, Antenna Engineer and Development at Kymeta Corporation in United States. Hand over to you, Mohsen.
Thank you so much, Fatemeh. Thanks for the introduction, I'll start sharing my slides so we can get started. Give me a second, please. Okay, hello everyone. Thanks for joining this session. It's a pleasure and it's an honor to be here and to be able to contribute to this session. What I would like to talk about today is how Kymeta has been able to take a metamaterial concept and turn it into a product that is being commercialized for satellite communication industry. Our journey has started in the laboratories of Duke University a few years ago, where David Smith, Professor David Smith, and his PhD student Nathan Kuntz were working on metamaterials. And they were working on different fields, but something that they realized that the metasurface concept has a potential for becoming commercial, for making its way into commercial products. So Nathan graduated from Duke University and joined Intellectual Ventures Laboratories in Seattle, and this is where they started a focused work on metasurface antennas. And his work there laid the groundwork for a number of startup companies. And so he became, later on, he became the founder of Kymeta, which is focused on SATCOM, in the SATCOM field. Echodyne is another sister company of us that is focused on radar communication, and Pivotal Conver is another one that is focused on terrestrial applications. It took Kymeta about 5 years to get to our first product and get the product out of the door. And what you're looking at here is a satellite user terminal. It's basically a scanned array antenna or a flat panel antenna, as we call it, that can communicate to the satellite as well as terrestrial network. So it's providing a hybrid solution. So the scanned array is being used for many different applications. Some examples are shown here, but our focus is really on land mobile applications, which come with very, very unique challenges such as cost, weight, profile, power consumption, and performance. When we look at our core technology, there are 4 different areas that stand out. The first one is the holographic beamforming, which provides the algorithm to be able to form a beam, scan the beam, and change its polarization or frequency dynamically. The second one is a diffractive metasurface, which is a radiative aperture. It's basically the hardware that implements a hologram. And it enables us to have a few features that I'm going to talk about later on, but one of them is to be able to do a full duplex antenna in one aperture. That's one of the nice features of the diffractive metasurface. The third one is the liquid crystal technology that is providing the reconfigurable mechanism to the metasurface, to the diffractive metasurface, to be able to provide the phase and amplitude profiles on the metasurface and be able to form a beam and steer a beam. It's also important to note that the liquid crystal technology is a key factor when it comes to the commercialization of the metamaterial, because that is a technology that helped us to get to a low-cost product and get to high volume manufacturing. Last but not least, software control, which connects all of the dots from creating a hologram, commanding the diffractive metasurface, controlling the liquid crystal unit cells, and forming a beam. But also, when it comes to pointing and tracking, this is an area where we have been extremely successful. I guess you're all familiar with the holographic beamforming concept, but here is a quick demonstration of how we look at it and the basic of our product. As you know, holographic beamforming is originating from optics, and this is where researchers try to find out how they can create a virtual image of an object without having the object. And what's happening here is that there are 3 components. There is a reference wave, and so it's the same concept that is applied to the antenna to microwave frequencies, where you basically have a reference wave, and in our case it's a guided wave, and you have a far field pattern that is basically the virtual image that we want to create in the far field. And you calculate the interference pattern that we call the hologram here with a simple equation. And so what that means is, when you look at it in hardware, we have a guided wave. It's basically a parallel plate waveguide on the bottom. And then the ceiling of the waveguide is basically the metamaterial. And you see a lot of pixels here on this metamaterial surface. And each pixel is being individually driven and individually controlled in its phase and amplitude. And by doing that, using that equation, you can calculate what that hologram has to be to point the beam in a certain direction. And that's how the dynamic beamforming is working. To take a closer look at the metasurface, here we're looking at an actual hardware of our antenna. It's the centerpiece of the antenna, where you see the metasurface. There are a few very nice features and advanced features on that the metasurface is providing that is making the product to stand out in the market. One of them, starting on the left, we have the polarization. And so the way we control polarization in software is at the hardware, the metasurface, is composed of cross-polarized pair of elements that you're seeing here on the left. So by having these two cross-polarized elements and by having the ability to control them separately, you can imagine that you can apply any phase and amplitude on these two components and basically create any polarization that you want coming out of these pair of elements. The other feature here is these elements these antennas are covering the entire KU band or the entire KA band. And in order to do that, we designed the elements to be able to tune all the way from the highest frequency to lowest frequency in the desired band, and that allows it to take any state that is required for that specific frequency. I mentioned that the full duplex is another feature of our antenna, and as you can see here, what we're doing in order to have a receive and transmit in a single aperture. What we're doing is we're interleaving two metamaterial arrays basically into one aperture, where you have the receive elements and you have transmit elements. And by doing that, we can simultaneously have receive and transmit from the same aperture. The last one is you can expand the concept of full duplex into a multi-beam, or where you now can have additional bands added or additional sub-bands added into this aperture, where each one could have a separate beam that is controlled and directed separately. So now the question for us was, how do we take this nice antenna concept and how do we move that and push that into a high volume manufacturing? And that's a hard problem to solve. But the solution for us was the LCD technology. The LCD technology provides two big benefits for us. The first one is scalability in size. And scalability in size is very important for us in our use cases, because we're talking about SATCOM antennas, and these antennas are naturally very large. We're talking about 80 centimeter or 90 centimeter apertures. And we had to find a technology that can produce this size of metasurface antennas or metasurface components, where each element is individually controlled. So that was the benefit that we saw with liquid crystal technology or the LCD technology. The second one is a volume, the scalability in volume. So if you look at the LCD market, there is more than 200 billion in capital investment on the ground right now that we have access to. So we're tapping into that market. We're tapping into that investment and into that available technology to get to the high volumes that we are interested in.
Sorry, Johnson, I interrupted. You have another 2 minutes.
Okay, I'll jump over a couple of slides to get to this slide. This is a closer look at our product. We have it's an exploded view where we have a radome on the top. We have the metasurface behind it, the TFT assembly. We have the feed assembly and an integrated modem and LTE behind it, and the RF chain on the back end. And you see an example of the antenna put against an FCC mask. And to conclude this very short presentation, the metasurface approach has resulted in practical implementation of metamaterial devices. The metasurface antennas have advanced features that are making it very competitive to classic scanned array approaches like phased arrays. And existing display technologies are enabling a high volume and large aperture production in our antenna use case. And with that, I want to thank the audience, and I'm happy to take any questions that you might have.
Thank you very much, Mohsen. It was really interesting. Thank you. We definitely back to you in Q&A. I personally have many questions from you. Thank you. Now I would like to introduce our second speaker, Dr. Mohsen Khalily. Mohsen is a lecturer in antenna and propagation and also head of Surface Electromagnetic Lab at University of Surrey, home of 5G and 6G Innovation Center. Mohsen, hand over to you.
Hello, Fatemeh, and thanks for the introduction. So let me to share my screen. So very good afternoon, everyone. My name is Mohsen, and it's my honor to be here to talk about industrial application of metasurfaces, the 2D counterpart of metamaterials. So basically, I'm working in 5G and 6G Innovation Center, University of Surrey, in which we have the largest research group for telecommunication in whole European countries. And one of the topics we are working here is we are focusing on surface electromagnetics, which we are dealing with the metamaterials and metasurfaces. So today I'm going to talk about the metasurfaces and what we have done so far in this research domain. So as a short and brief introduction, metasurfaces are basically the 2D counterpart of metamaterials, consisting of an ultra-thin planar arrangement of sub-wavelength size building blocks, which we call them unit cell or meta-atom. So they have a 2D structure, so that's why they can be easily integrated into the other devices and enable us to make the nano circuit and meta devices from microwave to optic regime. Also, they are able to manipulate electromagnetic waves. So in such a way, we can have blocking, absorbing, reflecting, transmission, or guiding the electromagnetic waves. So compared to the 3D metamaterial structure, they are capable of tackling some of the critical challenges rooted in traditional metamaterials, such as high resistive loss, dispersive behavior, narrow bandwidth response, and fabrication requirements for making 3D nanostructure. So there are lots of applications for metasurfaces. I'm not going to go, because of limited time, I'm not going through all of these, but thanks to my research team, we could design and develop different metasurface or metamaterial inspired antenna for different application. One of the interesting application is absorber. For example, from microwave to the optical frequency, absorbers are required in many applications, such as chambers, solar cell, photodetectors. However, the traditional ones are bulky and lossy. So metasurface-based absorbers are a good catch for their low profile and lightweight and simplicity for fabrication. For terrace also, this metasurface play an important role because to facilitate efficient and compact terahertz devices, a strong terahertz radiation matter interaction are required. So based on that, metasurface can help us to develop lens. They can help us to design and develop modulators, even terahertz source. And for 6G and communication, there are lots of applications which I will explain it in later. So the first design I'm going to present here is our Espar antenna, which Espar is actually electronically stable antenna, which is low cost and is a good alternative for beam steering compared to, let's say, like phased array, in which they require phase shifter. But as you can see, the conventional Espar, they are a bit bulky, and we should be careful about the limitation size between the driven element and the parasitic element around it. And they have a low front to back ratio, and they are not able to give us the dual band or triple band structure. So by using our method, which is inspired by metasurface and metamaterial engineering, we developed an artificial magnetic conductor to be kept close to the driven element to improve the front to back ratio, as well as we make the size as much as possible close to the driven element. So another difference between our approach, which is based on the metamaterials, and the conventional one, is for the conventional Espar, they need actually solid state devices like capacitor and inductors for beam steering. But here, just by simply turning on and off the diodes, we can steer the beam toward any particular angle. So we can suggest this and offer it for a steerable antenna for IoT application. So the next application of the metasurface, because in metasurface we are dealing with the surface impedance. So anything like lenses, even like OAM beams, we just need to calculate the phase and amplitude of each individual unit set. So here, what we have done, we developed one reflect array based on the metasurface to generate OAM beams. So for first time, we try to tilt the OAM toward different angles. So as you can see, with a very small size of metasurface, with just 20 centimeter by 20 centimeter, we could get around 20 dB gain, and also with the OAM, tilted OAM beams. So this can be applicable for inter-satellite link. So another prototype we have developed is a lens for near field focusing for 60 gigahertz, which we use the high-gain metasurface close by to a leaky wave as a source. So this one also has lots of application for automotive radar, radio frequency identification, reader, wireless power transfer. Also, it would be useful for communication over short distance. And one of the interesting application, which there is one prototype in the market based on this near field focusing, is for radiometric temperature sensor for hyperthermia. And based on the holography theory, we try to develop the one metal lens, which we put it in the SIWH plane horn antenna, the printed horn antenna. Basically, the printed horn antenna, or even the horn antenna, the bulky horn antenna, they suffer from the phase mismatch in a flare. So here, as you can see in the second picture here, down in the left side, we try to correct the phase mismatch by having a metal lens inside the flare. And as you can see, we improved the radiation pattern in a way that we get rid of the side of the level, but still there is a huge backlog. So we use the metasurface, the holographic metasurface based on the holography theory, to recycle the backward radiation and put them forward to improve the gain of the antenna and also improve the front to back ratio. With this compact size, we achieved around 11 something dBi gain. And this antenna is good candidate for V2V communication and for millimeter wave communication as well. The OAM one also, it was designed for Ka band from 28 to 31. So as I mentioned earlier, metasurface play a very important role in terahertz technology. So terahertz recently received lots of attention for telecommunication as well, from 100 gig up to, let's say, 600, 700 gig. But the definition of the terahertz is from 100 gig up to 10,000 gig, which is 10 terahertz. So we developed one graphene-based sensor, which can operate over a broad frequency range from 0.2, which is 200 gig, to 6 terahertz. So this sensor can detect materials with relative permittivity between 1 to 4 with a resolution of 0.1. And also this sensor can detect thickness from 5 micrometer to 600 micrometer. Besides, we also developed one novel spectroscopy technique to improve the sensing of this sensor. So this sensor has different applications, like medical application for cancer detection, and as well as chemical sensing. So another interesting application of metamaterials based on the artificial magnetic conductor is for GPS interference cancellation. So even metamaterials can play an important role in jamming and military applications. So here we developed a very simple antenna based on the AMC structure to combat blocking in GPS system. And as you can see here, F parameters have been improved by 30 dB. So another structure also, these work all are our recent work, and which I'm going to share with you, which to show the capability of metasurface to solve different electromagnetic problems. And as you can see, we develop any type of metasurface for different type of application. So this one is also for millimeter wave application, but for FMCW radar. Is based on the periodic leaky wave structure based on empty substrate integrated waveguide. There is a challenge here always in leaky wave to control the side lobe level at the same time and control the direction of the beam. But here we simultaneously been able to control the side lobe level as well as the direction of the main beam. So we improved the side lobe level to 30 dB based on the modulated periodic leaky wave. And but there is a huge interest recently in communication society on reconfigurable intelligence surfaces. These reconfigurable intelligence surfaces are actually the electromagnetic surface. So they are capable of flexible manipulation because we are going to deploy one in one metasurface. So let's imagine there is like a huge obstacle between the user and the base station, and we have some blind spot in any place. So by instead of adding a new base station or use other type of communication system, we can simply coat one wall, let's say, with one reconfigurable intelligence surface, which is one metasurface, and all of these unit cell or RIS element can be tuned. Their impedance surface, their surface impedance can be tuned by any individual control unit. And for millimeter wave especially, because millimeter wave rely on line of sight communication mainly. And so this will enable non-line of sight communication for millimeter wave. So there are few actually startups which working on these intelligence surfaces, but yes, there are lots of universities around the world doing research in this topic. But we've been the first group in the world that we've been able to practically developed and test intelligent dynamic metasurface in real world scenarios. So we have developed these two for 5G and we at 3.5 gigahertz. So one of them is dynamic and without any input power, and another one is a static one in which can.
Sorry, Mohsen, to interrupt. You have another 2 minutes.
Yeah, thanks. It can follow the user as well. So this static one is based on the holography theory. We can generate two different beams toward different diagonal, because in telecommunication, in network operators, for example, they facing two problems. One is power and another one is coverage. So sometimes if we know the blind spot, so just simply we can coat one wall with a large metasurfaces to provide the coverage. So at the last slide, based on this concept, based on the metasurface concept, for improving the coverage inside the building, we can develop, we already developed one transparent metasurface, which can simply coat it on window to make multifocal point inside the building. So this example is for 3.3 to 3.7 gigahertz. Also, we have developed another one for millimeter wave for 26 and 28, because European country using 26 for 5G and US and Asian country using 28. So it is a wideband metasurface, transparent with a passive and compact size. So this was, and actually I also sent a video, the link for our demo. I would actually recommend and to watch this video to get the flavor of how these intelligence surfaces are working and how we can use them in real world scenario. Thank you, Fatemeh. I think it was my last slide.
Thank you very much, Mohsen. Thank you. It was really interesting. Thank you. Now, our third speaker is Professor Alexandros Fercidis. Alex is the professor of microwave and terahertz communication and also head of metamaterial engineering laboratory in Birmingham University. Hand over to you, Alex. Thank you.
Thank you, Fatemeh. Thank you for the nice introduction. So let me just share my slides. Right, so hi everyone. So today we'll be talking about our just a brief overview that I'm going to give on our recent research on microwave to sub-terahertz metasurfaces and antennas for communications and sensor applications. So as Fatemeh mentioned, we have the Metamaterials Engineering Lab, which is part of the Communications and Sensing Group at the University of Birmingham. And we have over 30 years of expertise in antennas, metamaterials, propagation, and various microwave devices. For the last several years, we've been working on metamaterials-based antennas. And recently, we're focusing on antennas that can be used for 5G systems and beyond 5G systems. I will show you briefly some of the designs that we have on beam-steered antennas for millimeter wave frequencies, but with a technology that can be scaled all the way up to 1 terahertz, really, and could also be developed as an ultramassive MIMO type antenna. I will talk about tunable metasurfaces that we have also developed, designed, and fabricated and tested. These are the type of surfaces that can be used for intelligent, reflective, or reconfigurable surfaces, as was mentioned in the previous presentations, for 6G systems. And in developing these metasurfaces, we use some relatively new tuning technologies up to 300 gigahertz, and I will show some of these results. And also we're working on millimeter wave and terahertz sensing hardware and algorithms. And also we have microfabrication facilities. So we can actually microfabricate all these structures all the way up to 1 terahertz and test them. So this is just a photograph of our clean room. We have our own clean room, which is a 10,000 plus clean room, and that's where we actually fabricate all of our high frequency devices. And we also have test equipment that goes all the way up to 1.1 terahertz. So that's a VNA together with a quasi-optical system where we can actually do quasi-optical measurements and characterize metasurfaces and characterize materials and so on. So this is one of the projects that we have been working on for the last few years, funded by EPSRC. So as part of this project, we developed beam-steered antennas for millimeter wave frequencies, but also all the way up to sub-terahertz frequencies, up to 280 gigahertz. So the idea is to use a relatively new tuning mechanism, which is based on piezoelectric materials and piezoelectric actuators. So we actually, in effect, we developed an antenna which is electromechanically tuned, and we achieved tuning of a beam scanning performance up to plus minus 30 degrees. More recently, I think we have more than 40 degrees actually, with a gain of over 26 dBi and a very good efficiency. One of the main challenges at tuning structures, antennas, especially, or metasurfaces at millimeter wave frequencies or higher frequencies is the fact that you might have problems with losses. So with this electromechanical type tuning that we introduced here, we have very, very low losses, simply because the piezoelectric materials do not really interfere with the electromagnetic radiation coming out of the antenna. So you can see here on the left the operating principle of the antenna, some radiation patterns showing the beam scanning performance of the antenna. These specific results are at 208 gigahertz, are the most recent results. However, we have developed this antenna for 26 gigahertz and also 35 to 37 gigahertz. And this is all published on this in this iterative retraction paper that you can see down here. So on the right-hand side, you can see, you know, the model of the antenna. It's a metasurface-based antenna fed by a single feeding point, which makes the whole design and fabrication complexity very easy. So we have also worked on reconfigurable metasurfaces that could be used, for example, as intelligent reflecting surfaces and so on. So we have developed these surfaces at 50 gigahertz and also 300 gigahertz, again with very low reflection losses, which is one of the main challenges at these high frequencies. We achieved full 360 degrees tunable phase shift. So when you have a transmitting antenna illuminating this metasurface, and then you measure the receiving signal, the reflected signal, you get a full 360 degrees phase shift with very low losses. On the right-hand side, you can see the photograph of a prototype that we've, a macro-fabricated prototype at 300 gigahertz. It's based on essentially gold elements on a quartz substrate. More recently, we developed another type of dynamically tunable metasurface. This time, this is a fully electronically tuned metasurface using diodes, and specifically Schottky diodes, which are very suitable for high frequencies, all the way up to terahertz frequencies. This was part of another EPSRC funded project, which is about to finish, and we're using world-leading air-bridged Schottky diodes, which are provided to us by an industrial partner, Teratech Components, which is based near Oxford, here in the UK. So we have developed a prototype at 50 gigahertz, which again is scalable to even higher frequencies, and we're working on that at the moment. We have achieved over 200 degrees phase shift, but with our more recent designs, we can achieve the full 360 degrees phase shift, which is normally required in order to design a fully capable, maybe a kind of reflect array antenna or an intelligent reflecting surfaces that is able to redirect the beam to any type of angle. So this was again published very recently. On the left-hand side, you can see the unit cell and the diode which is incorporated within the unit cell. You can see the phase response for different bias voltages of the diode. And on the right-hand side, you can see an example of how the beam can actually be controlled and be directed to different angles. So we not only design these antennas and metasurfaces, but we can also do the whole transceiver essentially, where the antenna is actually integrated. So as part of another EPSRC project a few years, very recently, a few years ago, we have actually designed transceivers for very high frequencies. This one specifically is for 300 gigahertz. This is all based on waveguide technology, and we can use our antennas actually to test them within a transceiver structure like this. At the bottom here, you can see a metasurface-based antenna that was designed at 300 gigahertz and was used, and it was actually tested. You can see the test setup on the right-hand side, and that was all these measurements were actually at around 300 gigahertz. Finally, we're currently working on several new designs, and we're filing some patents at the moment on technologies for reconfigurable metasurfaces and antennas for full two-dimensional beam steering, starting from lower millimeter waves, 26 gigahertz and 40 gigahertz, all the way up to 300 gigahertz or even higher. Some of our technologies are actually scalable to very high frequencies, which is of course of interest for the new 6G systems, which are envisioned to operate over 100 gigahertz. So we're working on some new metasurface designs based on ferroelectric substrates, microfluidic technology. We also have studied liquid crystal materials and also Schottky diodes, as I just shown in the previous slide. These designs are based on some novel unit cells which are able to achieve maximum reconfiguration with minimum losses. And of course, all these different technologies have different advantages and disadvantages in terms of losses, switching speed, which is another important factor depending on the application, cost, ease of integration and fabrication, and so on. So we're working on some designs similar to the ones I've shown before, but also we're working on some transmit array designs, which is basically a concept based on the fact that you have a surface which is fully tunable and you put it in front of an antenna, and not necessarily a horn antenna, as I've shown here. That could be another kind of a planar antenna. That's what we're working on at the moment. And this transmit array surface can actually steer the beam by adjusting and tuning the metasurface. You can steer the beam and scan it in 2 dimensions. So this was my presentation. Thank you.
Thank you very much, Alex. Thank you. It was really informative and interesting. I will back to you definitely for Q&A session. Now, finally, the last speaker, but not the least, is Dr. Darren Cadman from CSA Catapult. Darren, currently, he's a senior bid manager in CSA Catapult. Hand over to you, Darren.
Thanks, Fatemeh. I'll just set up sharing the screen. Easier said than done. Can you see that okay?
Yes, yes.
Okay, excellent. So yes, I'm Darren Cadman at the Compound Semiconductor Applications Catapult. And I'm going to give a bit of an overview of who we are, what we're doing, and focusing on the RF and wireless comms area. So we've got our headquarters in Newport. We were set up in 2018. We began operations there with core funding from the government of 53 million. And we're up to about 100 staff and growing. Now, our vision there is for the UK to become a global leader in developing and commercializing new applications for compound semiconductors. To date, we've been involved with over 160 million pounds worth of collaborative R&D. We're one of 9 not-for-profit UK government-created catapults. And I should highlight that our focus is on the application of compound semiconductor technology. We're not a fab. We don't produce semiconductor chips. As with all the catapults, our remit is to engage in R&D, collaborative R&D, to accelerate the adoption of and de-risk compound semiconductor applications technology. And we do this through various funding streams, not just Innovate UK, but there's a range of domestic and European funding sources that we do this with. And our aim is to take things up that technology readiness level scale and to the benefit of UK industry, PLC, and the GDP. In order to deliver this, we've got excellent capabilities and facilities already in design that span across technology themes of packaging, power electronics, photonics, and lastly, RF and microwave. And all of these themes, these areas have got dedicated labs. And focusing on the RF and microwave and photonics, we're actively engaged in supporting the sectors of communications, defense, security, space, and transport. And as we've probably heard a lot over the day and in other sessions, this wireless communications and wireless infrastructure is becoming ever more present within our lives. And the subsequent pressures upon the technologies, increased bandwidth and higher efficiencies of the devices, for example. In terms of what capabilities we've got, the Catapult, it spans from everything from the device level, the circuit design, all the way through to the antenna. It's really that RF front end. And I think that possibly as Kevin Mitchell from Kinetic highlighted today, you know, you can't operate with these metamaterials in isolation. I think we try within everything we do to adopt an approach of looking at it from a system level. So we're looking at things all the way through from the chip through to how the waves are launched. There's some examples there of the areas that we can help with, and it does span all the way from if you're a small SME and you don't have the bandwidth to engage with writing the bids or even managing the projects if successful, the Catapult can facilitate those aspects as well as the actual technology development as well during the project. Specifically within the RF and microwave area within our group, the kit that we've got all aligns with a model of operating, of modeling, characterization, integrating and validating all at the system level, taking those gallium nitride or silicon carbide chips into the system and optimizing that system, that RF front end. And as an example, we had an internal program of how all these things come together. This was pulled through research from Cardiff University. It's a beam steering array demonstrator. And again, you know, you've got powers of over 20 watts output power, okay, under 7 gigahertz sort of operation. But there's a lot of heat to extract. There's thermal management and modeling. There's the device design, there's the antenna design, and the whole packaging, and the electromagnetic simulation. And beyond that, as another example, so that I'm starting to now move into more of how we can collaborate and work with organizations. So this is work done by master's level students at the University of Bristol, looking at beam squinting reduction of leaky wave antennas with metamaterial designs. Again, we can work with master's level students, but as a knowledge hub, we can also take on knowledge transfer partnerships as well and be a host institution for that. It's a real whistle-stop tour for myself, but these are the ways that we can engage with organizations. We can help with identifying the funding bodies. We can help with scoping out the projects. We can help out with actually creating the supply chain, which is essential to making sure that technologies do get adopted. We can support organizations with the project and bid management. We're developing our skills delivery so that we can support the development of the engineering capability within the UK. And of course, we can also engage on a commercial basis as well. I hope that gives a bit of an overview, a bit of a flavour in terms of what we can do from an RF and microwave perspective for you all. Thank you.
Thank you. Thank you very much, Darren. Thank you. And thank you to finish it on time. So many thanks to our amazing speakers who gave us some excellent insight into the metamaterials antenna and the advantage and how we use of current and future technology. Before we open up the question from the Q&A box, I would like to ask a question from our speakers. First of all, I want to ask a question from Mohsen Sazegar from Kymeta. Mohsen, could you please, and feel free all the speakers to turn on their camera and involve to the discussion. Mohsen Sazegar, could you please tell us about, because you know your company was successful from a novel idea to the product level. Could you please tell us in your journey so far, how did you initiate engagement and collaboration of to develop and innovate idea toward the product? And what was your challenge? Of course, I know that you faced a lot of challenge.
Yeah, that's a great question. As I mentioned earlier, it took us about 5 years to get to our first product and really roll it out of the door. And there were a lot of different challenges we had. We were trying to find the right technology that can make the antenna, but we were developing the concept at the same time. We were trying to find out, you know, who can make it, what is the best technology. We had actually started on using PCBs and liquid crystal, which wasn't a great idea. So once we had that switch to liquid crystal display technology, things got a lot easier because we were leveraging an existing and well-established technology. Does that answer your question?
Yes, yeah, thank you. And Mohsen Khalily, could you please tell us about how can Metamaterials antennas solution make a breakthrough in 5G and 60 millimeter wave limitation? Because I know in your center you are doing a lot of about 5G and 60.
Thank you, Fatemeh, for the question. Actually, when we talk about the millimeter wave, yeah, millimeter wave range can provide a good solution for coverage, for capacity. But they suffer from high pass loss, and the communication is mainly rely on line of sight communication. So if you really want to employ these millimeter wave systems for 5G or beyond 5G, we need to think about how we can make the blockage invisible, because if we can do that, we are going to actually enable non-line of sight communication. So metamaterials, popularly known as the thing they can make things invisible. So in my slide, actually, I presented one Metasurfaces, which they can enable the non-line of sight communication. So one of the, I think, promising new entity for wireless communication, for coverage, and even capacity is this kind of Metasurfaces. Another application for 60, as you also mentioned about the 60, we go to higher frequency like terahertz from 100 gig above. For those one, we definitely need Metasurface as a source, as an antenna, as like circulator. Lots of application will come when we discuss about the 60. And the last point I can mention is having transmission Metasurface to coat on window to improve the millimeter wave coverage for 5G systems. And another point we can discuss is satellite communication, because satellite is also one key entity for 5G, to deliver the 5G. So also for satellite antennas, we can use Metasurface flat antenna. I hope it was enough.
Yeah, amazing. Thank you very much.
Thank you.
And Alex, what you think, what infrastructure are required in the UK to turn the university research project into the commercial product? Because I know your group that are working very closely with the industry. Just wants to know your opinion.
Yeah, sure. Yeah, that's a very good question. I mean, in terms of infrastructure, I think there is enough in the UK in terms of fabricating and developing the technologies that's required to develop a product. I think it's important, however, to be able to transfer ideas from universities to industry. And for that, it's very important to have good links between industry and university, which sometimes, maybe especially in the UK, that's not really very straightforward thing to do. I've been doing that. I've been trying to do more and more of that the last several years. But I guess what you need is, because it's a two-way interaction, you need people from the university to be able to work on applications that are actually something that are very interesting for industry. But also you need for industry to be able to talk to the universities, appreciate what they do, and then provide some support. So for example, if you like to file some patents within the university and maybe to create a spin-out company, one of the main things that you need to prove is that there's some industry out there which is actually really interested in, in your ideas, either directly to provide some financial support or in the near future to do that. So universities are kind of looking for this interest from big companies as a way of evidence that what you're doing is actually important, So I think this interaction between industry and universities is really important, because this will allow for big companies to do some kind of outsourcing of some of their R&D, essentially, and getting some really good ideas, because there's a lot of know-how and a lot of talent in the universities in the UK. I think that will be beneficial for industry in the UK, but also obviously for the universities and academics as well. Yeah.
Of course. Thank you very much, Alex. Thank you. And Darren, in your opinion, how can universities advances in metamaterial solutions help the industry to in current communication challenges?
I think that's again an interesting question. It follows on a lot from Alex. I mean, I think there's things whereby you've got excellent initiatives at, say, Exeter University with the Metamaterials network, signposting industry towards the academic base within the UK. You've got, across the UK, you've got some great ideas that are research-based, and there's almost so many, it's then having to channel down and identify which ones are the real good ones. And sometimes it's a case of, from an industrial perspective, trying to pull it out of industry, out of academia. It's industry trying to identify not just the right institution, but the right academic to work with. So I'd probably say that Mohsen and Alexandros, both here, they're communicating with industry. They're probably the ones that are going to be able to relate to quite well in terms of what industrial needs are there. And sometimes it's a case of needing to do more of the applied research rather than the hardcore academic research that goes into journal papers. I think that, in order to do that applied research, sometimes it's also finding the right funding source. So things such as recently the DCMS announced funding calls, for which Catapult was at the heart of, diversifying the open RAN networks for 5G, trying to get involved with those sort of activities, pulling together supply chains for that, and deploying them. And it's about a sovereign capability as well within the UK. And I think that if I may follow on from Alex a little bit as well, in terms of pulling those advances through from the universities towards industry, sometimes you've got to have the right culture as well to incentivize the academics to do that. And whether that's a focus on enterprise activities rather than hardcore research and rewarding them appropriately, or it's when it comes to spin out, like what they've got at, say, Oxford and Exeter, should we say favourable terms to incentivize academics or researchers to go through that spin out process and pursue it and commercialize it and take it out into the wide world and test it.
So thank you very much, Darren. Thank you. I think now let's look at some of the question in the Q&A from the audience, and also my other colleagues from KTN, Robert, Richard, and Kevin will helping me through the questions. Robert, do you want you go for the first question? Oh, do you have access to the questions? Or?
No,
Okay, I can read them. I think the first question is for Mohsen Kymeta. In order to enable fast switching beamforming, is it safe to assume that the challenge was to apply your active liquid crystal material over ultra thin thickness, for example, 500 nanometer or less? If so, is liquid LCD display technology cost effective at such precision? Yeah.
Sure. That's a great question to ask. And I didn't have enough time in this session to go into more details, but I'm happy to expand on that. Our Metasurface right now is being manufactured on actual lines that are producing LCD displays. So they're coming off from the same lines. And so we have validated that with, right now we are manufacturing with the third largest LCD manufacturer, Innolux. But we have validated our concept with other manufacturers as well. I think we have validated four other manufacturers before. And they can all do it. But in order to get our product to be able to be manufactured on those lines, we had to make a few changes. We had to basically tailor our design so that it can be implemented in those environments. So we can imagine that as having two glass layers with a liquid crystal in between. The thickness that we're talking about, the thickness of the liquid crystal that we're talking about is 2 to 3 microns, and that's a right range to give you a switching time of 10 to 15 milliseconds. That's typical for LCD. These are typical thicknesses for LCDs. And that's what we are using too, and that's our switching time as well. So 10 milliseconds to 15 milliseconds, that's the range we're talking about. So one of the differences that we had to make, one of the changes we had to make, or one of the differences between our antenna versus a display is the thickness of metal. Obviously, at RF, you need skin depths. And what we're trying to do, so when you look at the LCD, typical metal thicknesses in LCDs, they're talking about less than 500 nanometers. What we need at KU is something in the range of 3 to 4 microns. So what we try to do is we try to stick to something that is higher than 3 skin depths, so that we don't introduce a lot of losses in the metasurface. So 3 skin depths, and that seems to be feasible. They had to, the LCD manufacturer had to make some changes in their process to be able to grow that thick. This is, 2 micron or 3 micron is pretty thick for an LCD manufacturer, but they are able to do it. It's adding a little bit of a cost, obviously, but we're still talking about a reasonable cost for an LCD panel. And the yields are pretty good. These LCD lines are optimized for yield, optimized for high yield, and the reason for that is when you have a display, you can't have any dead pixel in the display. So they really have optimized their process to have a really high yield. And when you look at our antenna, the antenna can lose up to 1% of the pixels without seeing any impact on the gain. So our requirements are different, and we don't have those harsh requirements that the LCDs has, and because of that, our yields are pretty good.
Thank you very much, Mohsen. Thank you for your great answers. Thank you. Robert, do you have access to the question now? Maybe you can.
Yeah, I can. There's one addressed to Alex. Alex, you've given a great presentation. Question to you is, what is the smallest structure? What are the smallest structures or critical dimensions you can currently fabricate? And have you used any ceramics? So dielectrics for higher power applications and further miniaturization.
Yeah, thank you. Yeah. So in our clean room at the moment, we can go down to about 20 microns in terms of the smallest dimensions we can fabricate. We can push it to even less, but I think this is more than enough for the kind of frequencies that we're working on. So we're aiming to, at the moment, we're working up to around 300, and we're aiming to go to sub-terahertz in existing projects. So this kind of capability that we have is more than enough, even for sub-wavelength metasurface type of elements. And in terms of materials, we have used different dielectrics, and we have used ceramics, but basically for lower frequencies in the past. We're not looking a lot in terms of miniaturization, to be honest, because of these high frequencies. Miniaturization is not really a huge issue in terms of what we're trying to do. And in terms of high power applications, yes, I mean, we are aware of, in some applications, high power could be one of the requirements. We're not kind of working on this too much at the moment, because we're aiming at relatively low power kind of comms kind of applications. But there are some solutions for optimizing for more high power applications that we have worked on in the past. Yeah.
There is a question on, and Richard, you're probably best placed to answer this question, is on why it would appear that university research, Catapult are focusing on government priorities. Why don't commercial industries have an easier way to communicate their needs to universities?
Thanks, Robert. Yeah, indeed. Hi, I'm sort of KTN's 5G guy, if you will. So sort of working on the DCMS program that Darren alluded to. It's primarily because the government and industry, if you will, have different problems. They own different problems. So from the government, the issue is around connectivity and capacity and capability as a societal and infrastructure, as a sovereign resource. It's also the case that the catapults are the spawn of government, if you will. And so there are those existing relationships. There's a well understood mission by the catapults to reach out, to draw that sort of research through to address those sorts of problems. Industry, on the other hand, has day-to-day problems. There's a capability that they don't have. That's the sort of issue they want addressing. And I think there's probably a perception in their minds that the sort of HEI research is a bit way off to meet their more immediate needs that are going to have a reflection on the next quarter's balance sheet and things like that. I think that's where things like BEIS's Industrial Strategy Challenge fund activities, where DCMS's digital strategy funds have been helpful and do have a role to play in helping those relationships gel and moving things on. I'd also stick in a nod to KTN's IX platform, whereby OEMs rock up with one of those problems that they want fixing and sort of cast that open. And we do get good engagement from universities on that. Indeed, we're assessing some at the moment, and I was up to my armpits in Fresnel matrices, which I love. So yeah, they do have different attitudes. Perhaps we need to understand the nature of government and industry's asks of AGIs a little more clearly.
Thanks, Richard. So another question here, and it's on energy savings has had a higher priority than radio frequency. I'll address this to Mohsen Khalily. So energy saving has had a higher priority than radio transparency over the last 30 years. And the result is most window glass is 30 decibel, alternating to 5G. When will the public be wanting more radio transparent windows?
Yeah, that's a good question. Actually, because of limitation we have, because I had just only 15 minutes, so I was not able to explain very well. We had another project on this energy saving using the metasurfaces. That's the one thing. But it's not actually 30 dB attenuating, but if just let's imagine we have 30 dB attenuation for millimeter wave, still we can have transparent metasurface to solve this issue. Because when we go to millimeter wave, basically there is a huge loss from the walls, and the only way we can get the signal through the building is the windows. So even if we have 30 dB loss from the window, these metasurfaces can solve the problem. There is one prototype from Docomo at 28 gigahertz, which is available in market, but they have some, like the efficiency is only 25%, and they can improve this coverage inside the building, but they are relying on repeater inside the house. What they did, they designed a lens which is transparent. You can simply coat it on your window. You don't need to change the window. But then after that, you need to locate and place one repeater at that focal point to repeat the signal with active elements. But what we have done at 6GIC, we don't rely on repeater. We developed a new technique to have multifocal point somehow based on totally infinite multifocal point, which really would be some game changer compared to the state of the art.
If I could just butt in at this point, I actually designed Metasurfaces to assist in the transmission of radio waves through various types of walls and similar structures in the 1990s. So it's not a new problem, and the solution back then was Metasurfaces, preferably on both sides. I should also say that transparent metasurfaces for control, and that includes the stopping of radio signals through windows. Again, that was done about 2004 quite extensively. So we do have a background there. But I agree that the use of higher frequencies for spatial multiplexing and for higher data rates is going to make the problem more acute. And it is probably something that we need to readdress.
May I chip in? Indeed. The attenuation of windows versus the thermal properties, of course. This is the sort of, if you will, sort of countervailing force. We want triple glazing. Indeed, I think, yeah, there's certainly scope for metamaterials getting signals inside. I also think that the energy efficiency of comms, wireless comms particularly, is going to come increasingly under the spotlight. IT comms currently accounts for about 3% of global carbon, if you will. and even the MNOs acknowledge that, yeah, 5G has wonderful grinning potentials, but as it massifies and rolls out, that's going to put an increased demand on. And we've yet to really look at the optimization of these new radio networks. And so I think particularly with the utility and economy that you can get from beamforming technologies is going to go a long way to mitigating the carbon cost of new radio comms imminently.
Yeah, I think there's an interesting trade-off to be made between thermal efficiency in terms of the houses we're all, or the offices we're all sitting in, and the cost of deploying, whether it's a carbon cost or a financial cost, of deploying new networks for 5G and 6G. If you look at the costs associated with 5G for new networks able to support these high frequency communications links, it's enormous. So it's actually something we've been thinking about at Kinetic for some time. Perhaps we should take further. If I may speak a bit more, then I just wondered what the rest of the panel thought about the imminence or otherwise of more advanced concepts around antennas going beyond the electrons sloshing around in bits of metal. Whether there is a market for new technologies of that nature, and if there is, how long is it going to take us to actually start exploring it? Deathly silence.
Okay, any comments? Any further thoughts? I think.
So, what kind of technologies are you referring to, Kevin?
Or self-assembling carbon nano fragments, whatever. Yeah, I mean and particularly the tunability. I love the liquid crystal stuff. It's predicated on a manufacturable technology, which I think is a key point if you want to get something deployed out in industry. But the tunability, that's a big issue. With the there are international standards around all these comms, and everybody uses frequencies slightly differently, which puts the cost of production of bespoke antenna for each of these territorial wave bands expensive. And terrible thing happen when you take it out of the box and it won't work because it's so yeah. Technologies to increase the wideband capabilities to conformable, reconfigurable micro antenna, and then when you get into sort of the massive cam sort of arrays, solutions there would be most helpful.
It's probably worth adding that, I mean, I did my first reconfigurable metasurface about 1995, sadly based on diode technologies, not the sort of advanced diodes that Alex is playing with, very much more commercial. So this sort of technology has been around for a long time. And we've got metamaterials antennas out there. Perhaps we haven't really touched on it in detail today, but if you look at sort of the kind of thing that the Kymeta guys have been doing, it's not just the fact that it's a good antenna, which it is, and it's reconfigurable and can do multiple beams and different frequencies, which is fine. It's also the fact that it's a fraction of the size, it's more efficient, it's not as heavy, and that's really important. if we are going to put them all in our vehicles and so on. So it's probably worth bringing that out in general as an advantage of metamaterial antennas. It's not necessarily always just the antenna performance, it's how you do it and how that benefits the platform or the comm system or the sensing system that you're dealing with. That's an important point, I think.
There is a question, Fatemeh, do you want to ask that one?
The last one.
Yeah.
Yeah, I'm really good at see which of the speakers like to answer. How engaged is the space industry with the development of metamaterials comms solution? Anyone wants to answer this question?
I can go first and give my opinion on this.
Thank you, Mohsen.
Since we are in that space, we're focusing on SATCOM, and so we're monitoring where the development of that the space industry is going and where metamaterials are being used to. I have seen a few instances where research has been done, or some applications from NASA where they're using antennas using metamaterials. But when you look at the mass volume of satellites that are being launched right now, through SpaceX or OneWeb and all of these LEO constellations, I have not seen any usage of metamaterials in those applications. Maybe I'm not. Maybe I've missed something there, but I think there is. The metamaterial needs more push to get into those markets as well. And I would be happy to hear from the audience here, from the forum here, to see what ideas you might have.
Can I go?
Yeah,
Richard, go ahead, please.
Yeah, indeed, I'd echo that. Again, we went round and we asked various sectors, sort of in the UK, what's your spectrum requirements over the next 10 years? And most of them said, what are you talking about? When we went to the space community, they gave us a shopping list. They know the wave bands they want and what they want to use them for. So again, they've kind of got those problem statements, if you will. I am sure if the metamaterials community approached them and said, whoa, we can get you out of a hole here in this sort of application, they'd willingly speak with you.
And so I can add to what Mohsen mentioned. For satellite communication, especially Ka band, we do need reflect array antennas, which based on the conventional one are a bit bulky, but Metasurface can solve this issue with like a compact, flat, actually reflector, which can provide high gain. Also, we can develop frequency selective surfaces based on the Metasurface, not the conventional one, because the conventional one trying to get half a wavelength the order of the unit cell, but here we are talking about the sub-wavelengths. So for radome, for airplanes, for example, in some particular application, OAM beams or different shaped beam, like we need to develop one antenna with a specific, like say, contoured beam, which is not, which is practically difficult to get it from the conventional array antennas. But with Metasurface, because we are dealing with lots of scatterer, which you can control any individual response of the phase and amplitude. So you can solve this problem. And I think in satellite communication, Metasurfaces can be can play an important role, because yeah, metamaterials antenna are different. Sometimes we mix everything, Metasurface and meta. They are somehow doing the same thing. But metamaterial, if we want like a real metamaterial, it should be 3D structure, which is bulky, which is somehow lossy. That's why we prefer to implement Metasurfaces in different applications.
Okay. I've been looking at the time. We've got a last question that's come in. Do any of the panel do research or have thoughts or concerns about the effect of increased numbers of and higher frequency of antennae on human health?
Actually, when we go to higher frequency, because the wavelength is smaller, so there wouldn't be like any concern about the frequency. Lower frequency is more dangerous, but any particular antenna we are going to develop or design, we have to look and study the SAVs, the specific absorption rate. And there are also the study around it. Of course, yeah, from the society, maybe there is some concern, but from theory and from the practice, because we developed like millimeter wave hybrid testbed at 6GHz, and we examined it in a real world scenario. We also practice and try to measure the emission of the electromagnetic wave for massive MIMO system as well. Yeah, I do respect this concern, but from theory and technical point of view, there is a way to control that, especially when you go to higher frequency, there wouldn't be any harm.
Thank you very much, Mohsen. Thank you. So is there any question or any comments, any thoughts you want to share, anyone? Because I think we have another 4 minutes left.
I have a question.
Yes, sure.
So for metamaterial antennae, what would you like to see to create a large market for the developments you're doing? What would you like, or help from consumers and users that are not yet engaged? What would you like from them? Apart from getting orders, by the way.
I think it's help taking all of the good concepts that, that we're working with at Kinetic, that academia is working with, and tackling that problem that the Kymeta people have had in getting from what is obviously a very good idea, and I've been following that project for a long time, getting it from a good idea to a product that you can produce in bulk. There's going to be a need for it, but it's getting over that difficult period between having the idea, having it demonstrated successfully in a lab environment, to something that's actually a viable consumer product. That's the difficulty, and it's really help in that region, I think, that's needed. Which I guess is the sort of thing that Innovate UK would be doing in general.
Yeah, well, it's pitching to to investors, whether it's public or private investors, and the end users, may want to have a skin in the game, so they want to invest early, so they'll be part of that market creation. So, what would you like from them? Thanks, Kevin. Yeah. I think you've got a minute, Yasmin.
Yeah, I think, yeah, we have just 1 minute left. So is there any final thoughts, final comments before we are closing up?
Okay.
Okay. Thank you very much, everyone, and thank you for our speakers, our panel, and also our audience that are with us for this last 1 hour. I think there is the session coming up at 4:30 from panel. You can continue to watch that one, if I'm not mistaken. And as I mentioned at the beginning, that this session is recorded and later on is available on the KTN website. Thank you very much and have a lovely day for everyone. Bye.
Thank you.